sklearn, linear model, SGDRegressor. Description: SGDRegressor implements a linear model trained by minimizing a regularized empirical loss function using gradient descent. The regularizer is a penalty added to the loss function that shrinks model parameters towards the zero vector using either L2 or L1 norm. This helps to prevent overfitting and improve generalization performance. SGDRegressor can efficiently learn from large datasets, especially when combined with appropriate learning rate scheduling. Inputs: X. This is the input feature matrix, typically a NumPy array or pandas data frame. Each row represents a data point, and each column represents a feature. Y. This is the target variable, which represents the values to be predicted by the model. It can be a NumPy array or pandas series. Outputs: self. The fitted SGDRegressor object, containing the learned model parameters, including weights and intercept. This object can be used to make predictions on new data. Core: the learned weights for each feature in the model. Intercept: the learned intercept term of the model. Steps: initialization: the model starts with random initial weights and an intercept. Gradient descent: the model iteratively updates the weights and intercept using the gradient descent algorithm. In each iteration, the model calculates the gradient of the loss function with respect to the weights and intercept, and then updates them in the opposite direction of the gradient, multiplied by the learning rate. Regularization during the training process. The loss function is penalized based on the magnitude of the weights L1 or L2 regularization. This helps prevent overfitting and improves the model's ability to generalize to new data. Metrics: mean squared error (MSE), a common metric used to evaluate the performance of regression models. It measures the average squared difference between the predicted and actual values. R-squared R2, a statistical measure that represents the proportion of variance in the target variable that is explained by the model. Higher R2 values indicate a better fit. Visualization plots: residual plot, a plot that shows the difference between the predicted and actual values against the predicted values. This plot can help identify patterns in the residuals and assess the model's assumptions. Feature importance plot, a plot that shows the importance of each feature in the model. This plot can help identify the most influential features and understand the model's behavior. Fine-tune parameters. Loss: the loss function to be minimized during training. Common options include squared loss, Huber, and epsilon insensitive. Penalty: the type of regularization to be used. L2 for L2 regularization and L1 for L1 regularization. Alpha: the regularization strength. A higher value indicates stronger regularization. Learning rate: the learning rate used in the gradient descent algorithm. A smaller learning rate generally leads to slower convergence but can help avoid getting stuck in local optima. Eta 0, the initial learning rate for the constant learning rate schedule. Powered: the exponent for the scaling learning rate schedule. Shuffle: whether to shuffle the training data before each epoch. Uncertainty methods. Confidence intervals: confidence intervals can be computed for the model's predictions. This provides a range within which the true value is likely to lie. Bayesian inference: a Bayesian approach can be used to estimate the uncertainty in the model. Parameters and predictions. Challenges and fixes. Challenge 1: slow convergence. Gradient descent can be slow to converge, especially on large datasets with complex relationships. Sample use case training an SGDRegressor on a large dataset with a high number of features and a complex target variable. Fixes: increase the maximum number of iterations max iter. Use a more efficient learning rate schedule in scaling or optimal Reduce the batch size. Consider using a different optimization algorithm, e.g. ADAM. Challenge 2. Overfitting. The model may overfit to the training data, resulting in poor performance on unseen data. Sample use case training an SGD regressor on a dataset with a high number of features and a small number of data points. Fixes. Increase the regularization strength alpha. Use a different regularization technique, e.g. L1 regularization. Use early stopping to prevent the model from overfitting. Consider using feature selection techniques to reduce the number of features. Challenge 3. Poor generalization. The model may not generalize well to unseen data, especially if the training data is not representative of the real world. Sample use case training an SGD regressor on a dataset with a specific distribution of data points that does not reflect the true distribution of real-world data. Fixes. Collect more representative training data. Use data augmentation techniques to create more diverse training data. Consider using a different model that is better suited for the specific problem. Challenge 4. Sensitivity to outliers. The model can be sensitive to outliers, which can significantly affect the model's performance. Sample use case training an SGD regressor on a dataset with a few outliers that have a significant impact on the target variable. Fixes. Remove outliers from the dataset. Use a more robust loss function, e.g. Huber loss. Consider using a different model that is more robust to outliers.